If there's one thing I've learned about light, it's that for unthinking energy, light seems to love messing with us. As I just showed you, scientists debated about whether it was a particle or a wave because it keeps exhibiting elements of both, seemingly unable to settle. Bizarrely, it behaves one way when you're looking at it, but a different way when you're not. But at least its speed is consistent. Light travels at the speed of light. No matter your frame of reference, that one thing remains the same. I have some bad news for you. It turns out the constancy of light speed might not be right either, and the next few experiments I'm about to show you proves it. Light might go slower than physics would predict in certain circumstances. And no, I'm not just talking about light slowing down in denser mediums like glass, although that's what I originally intended this video to be about. We have an explanation for that. I'm saying that in some circumstances, light seems to travel a path through time and space that has it either going slower or faster than the speed of light, even if dense mediums aren't present. But the really weird thing is that it ends up at the same destination in space and time anyway. Let me show you what I mean. Light travels at 299,792,458 meters per second. According to relativity, this is the only speed light can travel at, and interestingly, seems to stick to that number regardless of your frame of reference. Two people could be traveling through space, one at 1% the speed of light and the other at 50% the speed of light. But if they both look at the same beam of propagating photons, they will see them traveling at the same speed. Time and distance would seemingly rather warp than allow you to see anything other than light traveling at light speed. Of course, when scientists say this, they are only talking about light traveling in a vacuum. We've known for a long time that as soon as you get matter involved, light gets bogged down and travels slower. Light traveling in air only goes at 299,705,000 meters per second, a full 87,458 meters per second slower than light in a vacuum. Light in water goes around 225 million meters per second. Light going through glass caps out at around 200 million. The reasons for this are intriguing but fairly well understood, and certainly not physics breaking. When light travels through matter, its constantly waving electromagnetic fields gets the electrons within the matter to start moving, like ships bobbing on water. But as electrons moving up and down also generate an electric field that in turn creates a magnetic field, a second light wave is created by these moving particles that crucially overlaps the waves of the original light, albeit one that waves at a slightly different pace to the original light. Exactly what speed varies depending on the material. When two waves meet, they interfere with each other. They take an average, sometimes interfering constructively to build each other up, and sometimes working against each other. So when you take the grand total of all the ups and downs of each wave, you actually end up with a new wave, one that travels at a different speed to the other two, and one that goes slower than the speed of light. Eventually, this propagating wave can reach the edge of the blocking material, and without those electrons interfering anymore, you're left with just the original light again, which is then free to travel along its original path again, at its original speed, as if nothing had ever happened. Scientists have had a lot of fun with this concept over the years. Researcher Lene Howe at Harvard in 1999 was able to slow down light to an astonishing 61 kilometers per hour by sending it through a cloud of sodium atoms that had been cooled to 1/1000th of a degree above absolute zero. 2 years later, Howe managed to slow down light speed to 0 before warming up the cloud and sending it on its way again. You might find that result surprising. However, strange things have happened in the opposite direction too. In 2000, researchers at the NEC Research Institute in Princeton, New Jersey, sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse exited the cloud, it seemed that it exited before it had entered. While this might appear to mess with causality, how can you leave a building before you go inside it after all? Fortunately, there was a simple explanation that saved us from creating too many paradoxes. Although the light pulse traveled faster than light, the light itself did not. This was more an optical illusion than a refutation of Einstein's relativity. Let's take a closer look at a photon of light. As Einstein showed us, each photon represents a tiny packet of waves moving up and down. The speed the waves inside the packet propagate is known as its phase velocity, while the speed at which the packet as a whole is traveling is known as the group velocity. You can also have a wavefront velocity, which is how fast the first photon in a wave of photons can travel. This is a little heavy in its terminology, so let's explain it with an example. Think of a crowd of people doing a Mexican wave. The wave that the people are doing is the phase velocity. You can see the wave traveling along through the crowd. It might look like it's traveling quickly, but the crowd itself isn't going anywhere, so our wave's true speed is zero. These people are the group velocity, or possibly the wavefront velocity. Let's imagine that we wanted to send our crowd marching. They could do so and could keep doing a Mexican wave as they traveled. But although their waving hands might make the wave go really fast in the direction of their travel, it would vanish whenever it reached the front of the crowd. Information exchange couldn't go faster than the walking speed of the crowd itself, regardless of how fast the peaks in the wave seemed to be traveling. Einstein in relativity never claimed that phase velocity couldn't exceed light speed. He just claimed that information couldn't travel faster than light. And if you're trying to deliver a message to someone by sending a crowd of Mexican wavers in their direction, it really doesn't matter how fast they're waving. Until the first person in the crowd arrives, no information can be delivered. Still, this difference between the waves within light and the speed of light itself will become interesting in our next experiment. And this is where things start to get a little weird. Oh, you thought it was weird already? Oh no, this is the really physics-defying part.